Welcome everyone. I'm really delighted to introduce Trisha, our speaker for today, Trisha Mahoney. She's going to give her seminar is titled Removing Unfair Bias in Machine Learning. I had the pleasure of meeting Trisha at the Women in Data Science conference that we had here last spring, I believe. And it was just a wonderful gathering, and she was really instrumental in pulling that together. So that was a wonderful event, and we're delighted to have her here to give our first seminar of the semester. So Trish is an AI Tech Evangelist for IBM with a focus on fairness and bias. She has spent the last 10 years working on artificial intelligence and cloud solutions at several Bay Area tech firms, including Salesforce, IBM, and Cisco. Prior to that, Trisha spent 8 years working as a data scientist in the chemical detection space, and she holds a degree in electrical engineering and an MBA in technology management. So we're just delighted to welcome you. Trish, thank you so much for being our first speaker and kicking off our seminar series. And so I will let you take it from here. We will do some Q&A at the very end. Given this large group, let's limit our questions to the end of the seminar. So welcome, Trish. Thanks for joining.
Thank you. Thank you everyone for having me. So today our agenda is going to be an intro to fairness and bias. We're going to go through some of the fairness metrics and algorithms. So how do you measure and reduce bias? We'll go into some fairness guidelines, and then I'll do an interactive demo that can help you visualize what we're learning. And then I'll go into a Jupyter notebook on a real medical healthcare use case tutorial. So before we get started into the technical details, it's important to understand why we care about fairness. We know that human decision-making is flawed in many ways, and it's shaped by society's biases that can often be unconscious. So everyone thought that when we use data, and especially tech companies, if we use data to automate our decisions, it would make everything fair. But we now know that that's not the case. Evidence has shown that AI can embed our own human bias and deploy them at scale. So many experts are saying that bias may be the major barrier that prevents AI from reaching its full potential. And so, you know, for IBM, our biggest clients are healthcare and banks. So this is very critical to them before they jump into using machine learning and AI. And before I go forward, can you guys hear me okay? I just heard maybe some people were muted, but just want to confirm. Audio is good?
Yeah, excellent.
Okay, great. So first we have to kind of look at fairness. How do companies and industries even define this for their business problem? There are over 21 mathematical definitions of fairness. And these aren't just theoretical differences in how to measure fairness. There are different definitions that produce entirely different outcomes for your algorithms. So there isn't a one-size-fits-all definition for your organization. You have to define it for each use case. So, you know, for example, work was done by two leading researchers who found bias when they Google searched the word CEO. At the time, only 11% of the top image results for CEOs showed women, but women were actually 27% of US CEOs at the time. So for you as a data scientist, how do you determine what's fair, or the fair percentage of women that you would have your algorithm show? Would it be the percentage of women we actually have today, 27%? Or should the fair number be 50%? Should you show 50% women in your images and search? So those are some of the things that you have to think through as you're designing your models and dealing with your data sets. So, you know, many people in industry have heard of an algorithm called Compass. I'm not sure if you guys have all heard of this, but this was used to predict whether prisoners in Florida were likely to commit another crime if they went on parole. And after this algorithm was in deployment for a few years, it was later investigated and found that the algorithm incorrectly labeled African-American defendants as high risk at nearly twice the rate it mislabeled white defendants. And so this was, you know, heavily in the news, but what you don't often hear about is that Compass actually tried to eliminate gender and racial bias from the start. And the company who developed the scores claimed its system was unbiased because it satisfied predictive parity, which is a type of metric we're going to see. But it was later found that it didn't demonstrate balance for false positives. So this nuance in how they measure bias inadvertently kept many African Americans from going on parole and home to their families. Another example is Amazon's recruiting tool, that was recently, it had to be scrapped. The models were trained to vet applicants by observing patterns in resumes submitted over a 10-year period. And these resumes, especially in tech, were predominantly from male candidates because that's how the hiring decisions were made at the time. So this algorithm actually taught itself that male candidates were preferable, and it penalized resumes that included words such as women's chess club or women who came from all women's colleges. So Amazon really tried to address this bias and remove it, but they couldn't due to the complexities. So this is a very complex problem. So today what I'm going to use is IBM's AI Fairness 360, and it's just an open source toolkit that includes many different metrics and algorithms from researchers all over the world. So these are sort of the leading open source toolkits that are all in one space. And so before I jump into that, I'm going to look at quickly how you measure bias and where it comes from. So many people saw this image in the news, where does bias come from? You often hear of algorithmic bias as the issue, but the underlying data are most often the source of your bias when you're working as a data scientist. It's not the algorithm. So this can occur due to oversampling or undersampling, label bias, or user-generated bias. Something like if you're clicking on particular types of ads, when you're searching or on Facebook, you're going to continually see those types of ads. So that would be user-generated bias. So our models are trained on data from our past human decisions over many decades, and this can be reflected in our models. So in this case, we're looking at selection bias where one population was overrepresented in a training data set. And MIT identified this problem with all of the top facial recognition services, which had been predominantly trained on white male data sets. So this resulted in 99% accuracy for lighter skinned males and 65% accuracy for dark skinned females. So, the reason why so many tech companies pulled out of these facial recognition services was that, if your government is using facial recognition, the implications for a darker skinned individual, and the inaccuracies there are huge. So, a lot of data scientists often do this when I speak at events in different parts of the country. They may ask why I can't just remove protected attributes like race, gender, or age, or their leadership may tell them just remove these attributes and your model will be unbiased or your data will be unbiased. But you can't just drop protected attributes because there are too many features that are correlated with them. So even if you look at something as benign as zip codes, it would be actually very easy to deconstruct an individual's race or income by analyzing this data. Maybe not so much in Hawaii, but I moved from San Francisco 2 years ago, and I think if you use zip codes, you could still see different demographics easily when you break up the zip codes in a particular state. So I won't go into these things. These are some fairness terms you'll need to know to utilize the demo and the toolkit, and they're not part of a typical data scientist's workflow. But we're going to look at things as protected attribute and privileged protected attribute. These are things that you have to define for, say, race, gender, sex, religion. And then there are two types of fairness, group or individual fairness. And what we'll deal with frequently is fairness metrics and fairness labels. So I know this slide may look boring, but it's important. There are 77 different metrics, so we'll often use disparate impact, statistical parity difference, and equal opportunity difference. So it's just good to know from a statistics point, what does this mean? So for statistical parity difference, this is really the difference in favorable outcomes received by the unprivileged group to that of the privileged group. So, you know, if this was African American, 6 out of 10 had a positive outcome, and 7 out of 10 would be for the white. So you would measure this difference as 10% for statistical parity difference. Disparate impact is the ratio of favorable outcomes to that of the unprivileged group to privileged group. So that is how you measure this, which is dividing those two. And then the equal opportunity difference is the difference between the true positive rate between the unprivileged group to that of the privileged group. So essentially what we want to do when we're measuring bias is reduce these numbers, you know, these differences down to 0 as much as possible. The difference between, say, black and white, favorable outcomes between the two. And for disparate impact, we want this to be as close to 1 as possible. And that would indicate fairness in your data set or model. So one important thing to note is how you define fairness impacts how you measure it. So this is, you know, not the easiest thing. You can't really just give these types of decisions to data scientists, you know, and expect them to fix bias with math, essentially. So just to give an example of the types of decisions you have to speak with your leadership about is, in this example, do SAT scores correctly compare the abilities of my applicants? So if you were a university, you could say, you know, yes, I do believe SAT scores correlate well with the future success and correctly compare the abilities of my applicants. You would use a certain subset of metrics to measure bias. And you would go down sort of a different path or decision tree. But you may say, no, I don't believe that these SAT scores really correctly compare the abilities of my applicants. So, you know, some kids may be non-English speaking, they may come from lower income or single families, or, you know, often most lower income families don't have SAT prep that higher income families have access to. So there will be a difference in the types of fairness and the metrics that you use. And this really illustrates, you know, individual versus group fairness. So this is just a visual, I won't go into each, but it really shows that bias can occur at any stage in your machine learning pipeline. And fairness metrics and debiasing algorithms can be used at any various stage. But with that said, it's really recommended that you, you know, check for bias early in your pipeline, specifically at your data. And it's also recommended to integrate bias detection into your pipeline post-deployment. So continuously measuring for bias over time. And, you know, essentially, you know, you apply bias mitigation wherever you can intervene. A lot of the problems we have is, you know, when we're working with large corporations is we can't get access to all the data or the feature labels. So if you can modify the training data, then pre-processing algorithms can be used. If you can modify the learning algorithm, you'll use in-processing techniques. And if you could only treat the learn model as a black box and can't modify your training data or your algorithm, then only post-processing can be used. So I won't go into each of these, but these are just some different algorithms that can be used at different stages of the pipeline. And again, I want to reiterate that this toolkit isn't just algorithms and metrics from IBM. It's mostly from the top ethics researchers from around the world. So it's comprised of many different researchers' work and different toolkits. So I just wanted to reiterate again, pre-processing is the optimal time to mitigate bias because most bias starts with your data. And so you'll see that when I go into the notebook, the way maybe using pre-processing versus in-processing works with keeping the prediction accuracy high, as well as lowering your bias. And this is one of the last slides, but you're going to see in the demo, there are many trade-offs between bias and accuracy. Models really learn from the data that you give it. So you're responsible for building a fair set of data. So think about what your model is doing. Is it doing good things or bad things to people? If your model is sending people to jail, maybe it's better to have more false positives than false negatives. But if your model's handing out loans, maybe it's better to have more false negatives than false positives. You and your stakeholders have to determine the threshold for accuracy versus fairness based upon legal, ethical, and trust guidelines. So obviously you should do what's legal first, but that's, not all companies operate that way. You do need to, figure out what is ethical for your company. And lastly, when you do lose a customer's trust, for instance, like Facebook has recently, what is the cost to losing, trust in your customer base, which can be pretty high. And so this is the last slide before I go into the demo. But, basically for bias, it's very difficult. We're just scratching the surface, all of the large tech companies. So you have to work with your stakeholders early and apply the earliest mitigation that you can in the pipeline as possible. And you should check for bias as often as possible, using as many metrics that are applicable. So you don't want things like with the Compass algorithm to occur where they only measured bias in a sort of a narrow way. And again, because we're sort of just starting out with bias mitigation, you should use it with well-defined data sets and well-defined use cases. So with that, I'm just gonna show you, this is the AI Fairness 360 toolkit. So, you can access demos, videos, read a paper, use some of the tutorials, and kind of learn more on your own. Oh, let me alter my sharing of my screen. I gotta share the entire desktop. There we go. So yeah, this is the toolkit here. And, one of the things that's useful is the API documentation, where you can really get into the nitty-gritty of each metric or algorithm and have a good understanding of the equations behind that. So you guys can check that out after and look at some of the parameters, the raises, and the equations. So before I jump into that, I'm going to just do a quick visual demo. Let me just zoom in here a bit. So here we can look at, say, the Compass algorithm, the German credit scoring, or the adult census income. So I'm going to look at the Compass algorithm that we saw earlier, and this predicts a criminal defendant's likelihood of reoffending or repeating a crime. So pretending you're the judge and deciding whether someone should go on parole. And, originally this was developed to create more fairness, right? These algorithms. Many judges have shown biased decisions over many years. So, I do believe that AI can be used to, complement human decision-making to ensure that we are being fair. So for this particular case, sex is a privilege protected attribute. So the privilege class is actually female in this case, in terms of prisons, and the unprivileged class is male. Race is the other protected attribute. So the privileged class is Caucasian and unprivileged class is non-Caucasian. And so when I check for bias initially, before applying any debiasing, we'll see that the prediction accuracy is about 66%, but as it shows here in red, for the protected attribute of sex, there is bias in 4 out of the 5 metrics. And what this means is the decisions against men are more biased than women. And then for race, you'll see that there's bias in 4 out of the 5 metrics as well. So this means that the predictions that you're making are more biased for non-Caucasians in this algorithm. So what I'm going to do is apply the reweighing algorithm. So essentially, this changes the weights in each label combination differently to ensure fairness before classification. So actually, I should have gone back. If you scroll down, you can see with this demo, you can play with a few of these, so you can apply other algorithms across the classifier or the prediction set. But if we look at reweighing and go back and measure our results, we'll see for sex, we have reduced bias in 4 of the 4 previously biased metrics. So our prediction accuracy hasn't changed, but we've made the model much more fair for men versus women. And again, we've done this for race as well. And these are the metrics, kind of what I was speaking to earlier in the slide. So statistical parity difference, equal opportunity difference, average odds difference, and disparate impact. And again, this is, let me show you up here, before and after. You want to get these metrics as close to 0 as possible, and that would indicate, fairness. And for disparate impact, which is the ratio, you want to get this as close to 1 as possible. So that's how you interpret these metrics and bias measurement. Okay, I'm gonna take a quick drink. All right, so now what we're gonna do is look at how bias occurs in healthcare data and how we can mitigate it with AI Fairness 360. So this is called the medical expenditure tutorial. And just to give an overview of this use case, health insurance companies like to treat patients differently when providing managed care. So they'll use algorithms to look at patients and their data to prioritize cases for care management. However, in the US, whites utilize managed care more often than African Americans on average. And this propagates into our models as bias. And in fact, a model used on 200 million Americans actually included this bias. So we can't really just look at how much people are spending on healthcare to develop our models. But if we take a step back, why do African Americans spend less on healthcare than whites? And if you follow the news, Michael Bloomberg, I believe, donated $100 million to predominantly Black medical colleges. And so this actually ties into it. But, why do African Americans spend less on healthcare than whites? So there's a few reasons. African Americans may have jobs that don't allow them to take off, so they can't use their health benefits even if they have them. And doctors often treat African Americans with implicit bias and may not believe they are as sick as they report. So less healthcare treatment is often prescribed. And you'll see this in, say, women who are in childbirth. African American women actually have the highest death rate in the country. And it's often because of this implicit bias. So not believing that the patient is in the amount of pain that they state they're in. Another is that African Americans may not trust white doctors, so they may not trust the healthcare treatment that's being prescribed. So data suggests that African American patients do much better under an African American doctor than they do otherwise. So that really, the importance of Michael Bloomberg's donation that was brought up in the news today to medical schools that are predominantly Black is pretty important. So basically, if your data shows that a particular race spends more money and uses less healthcare, services, your model is going to be biased in predicting how sick a patient is and whether they need more managed care. So for you as a data scientist, it's important to ensure that there's fairness in healthcare models trained on past data, and to ensure that new data being created is fair as well. So what we're going to do in this tutorial is demonstrate bias in a healthcare classification model. We'll build a classifier using both logistic regression, and it's done in random forest as well, but you know, the random forests are similar, so I'm just going to go through logistic regression. And we're going to detect bias using 5 different metrics and do bias mitigation or debiasing with 4 different algorithms. And the data set used is called the Medical Expenditure Panel Survey. And this is the most complete source of data on the cost and use of healthcare and health insurance coverage in the US. So this is a very large scale survey of families, individuals, medical providers, and employers across the US. So that's our data set. And you know, the protected attributes we're going to examine here are race. So the privileged class would be white, and the unprivileged class would be non-white. And along with race as a sensitive feature, there are many other features used for modeling, including demographics, age, gender, active duty status, physical and mental health assessments, and physical limitations such as cognitive, hearing, or vision. And you'll see some of that as we go down. So the model classification task is to predict whether a person will have high utilization greater than or equal to 10 visits. And this is roughly the average utilization or visits to the doctor in the US each year. So let's see, did I show the features? I'll show that when we go down. So the steps we're going to take is we're going to look at 3 panels of data. So panel 19, 20, and 21. And these are people who are continuously monitored and sampled for a year in 2014 to 2016. We'll use panel 19 for training models, panel 20 for deploying and testing, and panel 21 for retraining. And then when we use panel 19 and deploy it in panel 21, you know, 2 years later, you'll see bias drift. So we'll then retrain with the new data from panel 20 to correct that drift. So first here, what we do is we import standard Python, the AI Fairness 360 packages, and we'll import the LIME explainers. And to simulate this scenario, we're going to split the data into the train, validation, and test sets. And then we're going to define that privileged and unprivileged class here. And if we look at sort of a quick summary of the data set, we'll see there's 7,915 patients in the training set, 4,749 in the validation set, and 3,166 in the test set. And these are some of the features I mentioned earlier. I won't go into all these, but there are many different features in this model. So first, what we're going to do is measure bias on the original data set. And so we'll do that here using disparate impact. And you'll see the number is 0.48. And this number should actually be much closer to 1. So this indicates that there's bias in your original data set. So if we go forward and train a logistic regression model, we can kind of go down and see the results. And what we find is that the prediction accuracy is good here. It's about 78% prediction accuracy, but all of these metrics here are showing bias. And this is in the test set, as well as validation set. So, so the point we're trying to make essentially is that the original data set is unfair and the model that we're using is unfair due to the data set. So I'm going to skip through the random forest model because it's basically the same steps. So now what I'm going to do is apply reweighing on the original data. And this associates a weight to each data point so that the final data set you obtain becomes more fair. So once you do this, just looking at the data set here, if we measure disparate impact again, after transforming the data, we'll see that it's actually 1. So this is very good. It suggests that there's fairness now in the data. So now we're going to train the model using logistic regression on that reweighed data. And again, we'll check for bias and accuracy. So we'll see here, the prediction accuracy just went from 77% to around 76%. So that prediction accuracy is good. It's an acceptable decrease. But what you'll see is that the level of bias measured has dropped by an order of magnitude. So much closer to 0, which indicates you have much more fairness. So again, we'll skip through the random forest. And now what we want to look at is bias mitigation using an in-processing technique. And so we're going to use the prejudice remover. And essentially, what we're going to do is train and validate that model again. And what this really does is look at changing the model directly by applying constraints. So again, the in-processing algorithms directly change the model itself versus what we did earlier, which is pre-processing, and that changed the data. So again, we're just going to go through those same steps and train, validate the model, and then check for bias. So in this case, the results are a bit different. We were able to reduce bias, but the prediction accuracy went from 77% to 68% prediction accuracy. And that's the same for the test set as well. So, you know, even if the fairness improved, you have to be careful on your approach that you use because this may not be acceptable to your business in terms of prediction accuracy. So this is just kind of a quick summary of what we did. You know, we had the original bias measurement with different metrics using logistic regression and random forest before applying the reweighing algorithms and the prejudice remover. And as you can see, our prediction accuracy has gone down a bit, especially for prejudice remover, but we have reduced bias significantly with these approaches. So what we want to do is check for drift after a year. And so we'll deploy the same model on panel 20 data. So this is going to be a 2014 model used in 2015. And what we'll find is that, you know, the prediction accuracy has just gone down a bit, and our bias is actually still pretty good. However, and I'll go back to this Lime explainers, if you use a model trained on data from 2014 and deploy it in 2016, when we come down here, you're going to actually see that bias drifted quite a bit. And so essentially, you know, not in the first year did bias start to occur, but in the second year. So really you have to go back and refresh your model with newer data and apply bias mitigation again. So just, you know, wanted you to visually see that. We don't have to go into each step, but it's important to see that, you know, we do need to do corrections for bias drift, not just accuracy drift, which is what most companies do today. So you'll kind of see this. You can go back and see this notebook later if you want to look at those results, but this is training with different panels and looking at the results over time. An important thing too that we look at is explainability, AI explainability. So I'll go back up to the Lime explainers here. And for you as a data scientist, or even if you have a nurse that you're working with, it's important to look at which features are really telling you someone has a high probability of needing more than 10 visits a year when they're going to the doctor. So these are just some of the features like chronic bronchitis, smoking, pregnancy, emphysema. And this is a different patient that we're looking at. What are the features that attribute, whether they're a patient that has a high probability of needing more managed care. So you can go into some of that documentation here for Lyme, but explainability and fairness are very much tied together. And you need to assess, actually with humans sometimes, to ensure that your models are performing correctly. All right. So I'm going to stop there. Gwen, if there's any questions.
Questions now? Okay.
Yes.
Okay, let's see. So I can moderate the Q&A. Let me get my thing. Whoops, sorry, I'm trying to find this screen of people. Okay, if anyone has a question for Trisha, if you could raise your hand, and I will ask you to speak. And I would ask you to please open your your display so Trish can see you. So let's start with Crystal Boyce Gudat. Go ahead, Crystal.
Hi there. I'm a PhD student in a communication information science program here at UH. I was curious, the bias mitigators, the algorithms that you talk about, and then the different data points in terms of what is privileged and what is not are all binary in nature. Mm-hmm. At what point do, if ever, the algorithms and or the data actually start to treat race, ethnicity, gender, and other points of discrimination as spectrum identities?
Yeah, I mean, I think it's tricky, right? Like, I'm Hapa myself, so what does the world see me as? That's really where a lot of this bias comes from. So I think, mathematically it is binary right now. You have to define one privileged class, and you can only do bias mitigation with one privileged group at a time, right? So it's tricky to say whites versus non-whites, because in a different city it could be something else. So it's a bit tedious. You have to check for each individual race at a time, but it's hard to say when this will all be one particular spectrum. Again, you can look like one thing, but you're actually a different race, right? So it becomes very tricky.
Great. Other questions? Paul Switzer.
Yeah, so my question is this. Let's say we want to remove gender bias, and we just treat the males and females as two different populations and train the algorithm separately on each group and apply the group-specific algorithm. Does that go anywhere towards removing bias?
I think it's tricky. As I was mentioning earlier, there are several features that are correlated to gender that you can't really just separate the data that way. So often, if you're hiring candidates, women will write differently about their qualities than a guy, right? Men will use very strong words like execute, spearheaded, drove this initiative, and an algorithm could say these are admirable qualities, but women would actually never say that. So the algorithm may raise it one way, but an actual human may look at that resume and say, this woman's a joke. What does she mean? She spearheaded and drove and executed all this stuff. So that human, they may say, oh, that's, they may have bias, and the algorithm may not. So I guess what I'm saying is you can't just separate data that way.
But if you're building a separate model to predict success in the job for females, it might not even consider some of those features that are sex correlated in predicting success for females.
Right.
In other words, suppose you just had a population of females, then you build a model to predict success. And some of those features that might be considered important for males might not even arise in the model for females.
Right. Yeah. I mean, it's tricky because there's so many different features. I know that Accenture is building specifically hiring platforms, but they do not separate male and female to do that. I don't have the full answers to all the research in that area, but typically I don't see our researchers separating data by gender. And a lot of times, the reason why this is critical, if we work with banks, which 50% of our customers are large banks, they'll never give you the data on race or gender. So, you need to remove that bias without that knowledge.
Right, thank you. Do we have any other questions I'm looking for hands going up here. Any other questions for Trisha?
And I can't figure out how to do the digital hand. It doesn't seem to be popping up on my screen.
Right, Paul,
Did I show my actual hand? I just want to double back, Trisha, to Crystal's point about continua. Seems like for the young kids, they're all going to want to be working on hypersurfaces or something, because so much of what you see is sort of defined in binary terms. And so 2 examples. One would be, at some point, we're going to know enough about genetic admixture so that the idea of, we have these buckets, and then they finally invented the hop a bucket, other, please specify, that kind of thing. The buckets themselves are the problem. And then another one you mentioned early on was, so I didn't take an SAT prep, but this was in the Pleistocene era. I don't even know if they had SAT prep when I was prepping for the SAT. But I found myself a little disturbed by the idea that an algorithm is going to make an adjustment so that would have changed the probability of my ending up on the path I ended up on. So, I mean, not all decisions are, the product of some social whatever. I was too busy surfing or whatever. I don't know what I was doing. It was 1972, it's like, so I'm just curious about this idea that Crystal raised about moving to, this is live long and prosper for, who is it who started up, I'm talking about, there's another mathematics out there that allows for, hypersurfaces and all this other stuff. And we can get away from these dichotomous.
Right. I mean, I do think it's important. Just for example, like I grew up very poor. I didn't study for the SAT at all before I took it. I went to college, and that was because my parents were not educated, right? And my husband had weeks of SAT prep and got a perfect score. So, you have to ask yourself the question, if that's how you're going to rate your students, you got to score them somehow. Is there some sort of bias, right? If you're letting women into engineering school, or if you're, within Los Angeles, I used to live in LA. It shocked me that UCLA, which is majority heavily Hispanic population, has 2% Hispanics in their university. I think we can say don't look at binary, but it's still very prevalent, right? And so algorithms are starting to decide who gets a home loan, who gets to go into a school, and now who even gets to go on parole. So we do need to ensure that there's fairness. So this is a specific way to sort of measure it. You know, the big thing is really measuring that bias. And again, ensuring that you have a very fair data set. Now, we looked at African American versus white in this healthcare scenario, but you know, in Hawaii, are Hawaiians and Polynesians treated equally by doctors who are not Hawaiian and Polynesians? So you can say we shouldn't look at these binary things, but you do need to ask yourself that question. You know, is it racially equitable in the type of treatment and attention they're getting?
Wonderful. Let's see, Crystal, you had a follow-up.
Yeah, just the way that you were talking about that last thing, I'm kind of wondering, like, how often are these predominantly used debiasing algorithms updated? So for example, you know, because you were talking about Hispanic ethnicities, that wasn't recognized by the census as a measurable thing before the 2000 census, right? So we haven't had the numbers since then. So like in terms of these debiasing algorithms, how often is somebody going back and tweaking it based on the new information, the new ideas, the new concepts?
So the debiasing algorithms and the metrics, most of them have been around for quite a while, especially the metrics, right? They're just mathematical equations that have been around for years. And again, they were kind of in the hands of a few ethics researchers, but they were never kind of coded into a way that could be used in a machine learning pipeline. So that's sort of what we've done with our toolkit. I mean, Google's doing it, Microsoft, Amazon, is sort of bringing these things that were just in research, mathematical equations, and putting them out into actual machine learning pipelines and building them into our algorithms. So again, it's really our algorithms that, you know, need the constant updating, but a lot of the other mathematics around it have been around for quite some time.
I think, thank you. I think Paul has a follow-up. Paul, did you have a follow-up? Paul Switzer? Or is your hand just?
No, I don't have a follow-up.
Oh, okay. All right. We're going to do a little experiment on this group. Maria's going to drop into the chat our optional demographics form. So if folks could fill that out, we'd like to collect that information as well. Let's see, any other questions for Trisha?
And I have some things I could put in chat too, if people needed those resources. Oh, can I send to everyone, or?
I think if you just put it in the chat message to everyone, it should show up.
There we go. Okay.
Okay.
And I could just share this really quick so you can see what I'm sending you. I mean, this is a very complex topic, and I don't have all the answers, nor does anyone at this time. So, you know, again, what we're really trying to push is getting data scientists to start looking at this stuff, right? Starting to measure bias and bringing it to the attention of their leadership. You know, honestly, with a lot of companies we work with, they don't actually want to touch bias yet. They do want to address AI explainability, but fairness and bias is still something they keep under wraps, but it does need to start being examined more heavily. And again, I sent this book. I wrote an AI Fairness O'Reilly book with other researchers, but this will kind of give you more information to just start to think about the topic. And I put that in the chat.
Wonderful. All right. Just looking for any last questions. I think we're good. All right. Well, any other comments you'd like to leave us with, Trisha? This was really wonderful. I'm looking at the chat and people are really enjoying your talk.
Yeah, it'd be just great to get some feedback. And, you know, I usually present at different events across the country, but, you know, not usually the students. So it'd be good to see if this was the right level of what you needed to hear, if there's other things that you wanted to hear about. So thank you so much.
Thank you. Okay, I'm going to clap virtually for you. Thank you so much, Trisha. Really enjoyed meeting with you, and also just stay in touch. I think we have your contact information. If folks want to reach out and get in touch with you, I'm sure that'll be okay.
Yes, definitely.
Okay, all right. All righty. Well, thank you all. This has been a wonderful start to our semester and our seminar series. So I want to wish everyone a very wonderful, relaxing, hopefully long Labor Day weekend. Stay safe and enjoy. All right. Thanks so much, everybody.